diverse group of people together. And hopefully I'm able to show you something that might appeal to you one way or the other. So I've taken Mark's advice to heart, and I'm not going to mention C-star algebras at all. I'm just going to talk about higher rank graphs, and the idea is I'll tell you what they are, and then I'm going to tell you how I found new ways of making them. And I think the lesson to be learned from some of this these talks is that finding higher rank graphs can be your work can be a good thing. So this is a part of my so thanks to Howard, I've already seen the definition of a higher rank graph, but let me so it's just a countable category with a degree functor satisfying a certain factorization property. And then there's a bunch of category theoretic notation, which happily has pervaded the conference to date. So I don't believe there's any difficulty in getting hold of that definition. The point being that the object of degree 0, the morphisms of degree 0 can be identified by the objects. That's the factorization property. So there's a nice relationship there that comes in very handy. Okay, and then factorization property also gives you some sort of a coordinate system inside your morphisms. You can take a m and n less than d lambda and then factorize it into any pair of numbers between 0 and d lambda, and so you can look at sections of your lambda restricted to some middle part of it. So this gives you a nice coordinate system for calculations and for makes life very simple to be able to do that. And by the factorization property, it's really because also the receiving object is end of the k. The rank graph is both left and right cancellative, and also to avoid some awkwardness, I shall assume that every basis vector of n to the k is the range of some morphism. Otherwise, it's pretending to be a high rank graph if you don't use up all the dimensions. So I'm looking at real high rank graphs. Okay. Then there's some technique. Oh, I should go back. Sorry, meant to go back. So let me just mention there are some newer definitions going around. I think one was mentioned today, a P graph. That's where you allow the receiving category to be an abelian group with some torsion groups. And I believe that theory is not well explored yet. So there's some interesting things to say there. Also, there's topological versions of this as well, which takes you quite a bit of a long way into C-star algebras. So I'm not going to go there too. But there's a few interesting generalizations of this definition, which are worth exploring as well, which I'm not going to touch on. So these graphs can have sources and sinks. So a source is something that doesn't receive any morphisms, and a sink is something that doesn't emit any morphisms. And if there are no sources and sinks, then lambda is essential. And I shall nearly always deal with essential graphs because basically it just keeps all the notation simple. And especially when you go into C-star algebras, there's a lot of baggage you've got to carry with you in order to make sense of things with sinks and sources. So I'll typically, and except for the one and example at the end, I will not be following that. And also, this also, yes.
I was wondering, is there a reason for the name Essential? Like, does it mean
Essential? Yeah, thank you, Becky. So a lot of my understanding and feeling for K-graphs comes from dynamics. And so the word essential comes from Linden Marcus, where Linden Marcus used directed graphs to define shifts of finite type. So quite often I want to use a higher rank graph to define a higher dimensional shift of finite type. So I'm just copying their notation. So that's the main difference. And again, because of Malcolm's talk, I shall avoid, like the plague, graphs that are not row finite. That means that every vertex receives only finitely many edges. That's already hard enough, I think. So I will like as simple as possible. Again, row finite, that word row finite comes from the matrix way of considering graphs. So that's where it comes from. Okay, the finite, and again, I think this has been pointed out in previous lectures. So because of the factorization property, if you've got a morphism of degree EI plus EJ, you can factorize it in two ways, because EI plus EJ can be written as EJ plus EI. And so you can factorize a given morphism as EF in one way and F primed E primed in another way, where the degrees have swapped places in factorization. And so naturally you get a lot of commuting squares in your higher rank graph. And in fact, I'm going to spend a lot of time today talking about commuting squares, because really speaking, the whole structure of the graph is contained in these commuting squares. That's why, unfortunately, I had to make it be small to fit in the picture. So the small commuting square. Okay, this is something that came up in Brita's talk and in several talks otherwise. So this, in some ways, is a very important two graph. And it was defined, first of all, by Power. And then Gillian Yang started working on them, and she's published a lot of papers since then in this direction. These are single vertex K-graphs, and if you think for a little while, a single vertex K-graph is going to be a monoid, because everything's composable, the identity being the vertex. And here's a way of conjuring up lots of them. So just for notational purposes, let brackets n be the set of numbers between 1 and n. Then what you need is the ingredient in the picture is a bijection from m cross n to m cross n. And then you take a monoid with generators m lots of f's and n lots of g's, where there are no relations between the f's and no relations between the g's. But whenever an f and a g meet, you can swap them round like so, according to the matrix entry for ij. So Fij equals to Fgj primed Fi primed, when theta ij is I prime j prime. So all the information, all the data is contained in this map theta. And in fact, you've seen this map theta many times actually during these lectures, with bijections between certain sets of values. So this is a model to be very useful, and particularly for the British example, which we saw on the first day. So let the degree of the f's be E1 and the degree of the g's be E2. Then since this factorization property doesn't change the degree, you can now use this definition to define the degree of any element by pushing all the e's to one side, the f's to one side, not all the g's to the other side, and counting them. So D extends to a functor, satisfying the factorization property, and so you get a 2 graph. And then if you are got nothing to do on the way home, you can convince yourself that every monoidal 2 graph appears in this way. Basically, you just work backwards. So, and these graphs show very important. Still, I think they've still got a lot to offer people who've been in the business and who are new to the business. Because what Brito was writing down was the Cayley graph of this monoid, where the pillar swaps are to do with this. So very important, and also you can do this in higher dimensions, but then we run into problems. And we've seen this problem occur several times in these lectures. Once you hit 3 dimensions, something goes wrong with multiplication. You've got to add this extra condition, which we refer to as associativity. No one's been brave enough to write it down, but it was written down in the talk before. It's essentially the Yang back. And so you run into very quickly run into a brick wall, because to find a free graph of such a thing, you've got to solve Yang-Baxter equations. So good luck with that. But I'll indicate ways of cheating maybe later on. Who said there are not enough K-graphs?
I never said that.
You just take n equals m equals 2. There are 9 non-isomorphic 2 graphs of this form. Basically, you just got to look at all the conjugacy types of bijections between 2 cross 2, 2 cross 2. Only 9 diagrams you can draw, like the ones I drew on the board. What gets really interesting, and this was thanks to I think did you have a hand in this? He credits you for this.
Only for the 9.
Only for the 9. Well done, you got it right. But for m equals n equals 3, there are over 3 million. Now, don't get too scared, because a lot of them are going to have the same C-star algebra. They're going to have similar algebras to each other, but they're different in terms of not being not algebraically not isomorphic as monoids. So they're different things. So there's a whole lot of these guys here, and it's very easy to write one down, particularly for a k equals 2. So that's one good thing. The next thing comes to us from the original paper. We let omega k be a category whose objects are the lattice points in the first quadrant. Okay. And you get a morphism between n and m precisely when n is bigger than m. Range is m, source is n, and composition is as you expect. And you get a k-graph for every n, every n, sorry. And this graph is very special. I'll draw a picture of it later, shortly. This graph is very special because it's the prototype for an infinite path. Just as the straight line of arrows, as Sarah drew in his book, is the prototype for an infinite path in a directed graph, this is the prototype for an infinite path in a k-graph. So it's a very important startup k-graph to get hold of. And then Raven Simjind produced a truncated version of it because they were interested in graphs that had sources. And so they had to use this to help define infinite paths, the graphs that had sources. And then to state the obvious, end of the K itself is a K graph. Then your degree function, the identity map. So there's a bunch of basic K graphs to get started with. And what I'm going to do in the second half of my talk is tell you how to mess around with these basic graphs and get more and more complicated graphs with higher and higher dimensions. Because as we've discovered, getting a 3 graph isn't a tricky business. And it's good to know ways of finding them or building them to your liking. And then I think people have talked about skeletons as well. So the skeleton is just the graph you form by using all the morphisms of unit degree. And you just draw a directed graph using them. That's what I call the skeleton. Now you can color that graph by remembering what dimension that edge was in and giving it a color. So what I'm doing is I'm giving you a way of writing down or drawing a picture of a K-graph as a colored graph. And anyone who looks at K-graph literature will quite often see pictures of colored graphs and perhaps wonder what on earth they're doing. What they're doing is they're giving you a visual way of looking at a K-graph and getting a feeling for its structure in a very compact and formative way. So this is what we're doing here. So you just give a color to the edges, and then that the graph together with the coloring is what I call the one skeleton. And of course, if you started with a K graph, then you automatically get a K color graph, which I'll call SK lambda, C lambda. Now let's forget all that and pretend that somebody's just handed me a colored graph. And they want to know, is this a K graph? Is this a 2 graph? Is it a K graph? And you quickly realize that it's not going to be always true. And so you're going to have to figure out how to check it. First thing to check it, most important thing to do to check it is the squares. Remember, I mentioned squares at the beginning. They really tell you all about the structure of the graph. And those squares have fit together in a very nice way. And so you've got to look for a collection of squares that fit together in the same sort of way that they do in a K graph. And then from that data, you can go back up to the K graph. So if you take a color graph, you can form squares using bicolored elements. So paths of length 2 that use 2 colors. And then you look at pairs with the same source and range, but with the colors switched. And you form a collection of squares. They'll form, draw the squares, red, blue, red. And so these are the canonical collection of squares defined by the skeleton, because it's the structure of E that allows you to write these guys down. And of course, in the K graph, we had this for free. I didn't mention it at the time, but you can see through the factorization property, which I talked about in the first couple of slides, you naturally get these bicolored squares. So they occur all the time. And so you should look very carefully at these bicolored squares and see how they match up with what happens in a K graph. And the important property is what's called completeness. So each a set of squares is colored if for every IJ colored path, there exists a CJ I color graph. So switch the colors around that such that pair lies in C, same source, same range. So in some sense, what's interesting is a path between vertices, paths of length 2 between vertices that go red, blue, and blue, red. There needs to be a bijection between those. Because of this. And again, the factorization property told us how to do this. But if you didn't have the K-graph to start off with, then this is obviously something you're going to want, because your target is K-graph. And the result by HRSW, so that's Hazelwood, Rayburn, Sims,
Webster.
Webster, thank you, tells us that for K equals 2, every 2-color graph with a complete set of squares uniquely determines a 2 graph. Now I should give myself a little bit of credit. Alex and I wrote down an argument, but I think these guys did a much better job. And what about K bigger than 3? Well, we run across the our old chestnut, the associativity condition. So there's an extra condition called the associativity condition, which again, I'm not going to write down. You can look it up in HRSW. This condition is for about squares that have, is about paths of length 3 that use 3 colors. And it's about the switching out those colors around in 2 different ways to build a cube. And I think somebody drew a picture of a cube with 3 colors going down 2 faces, and then using the colors in a different order, you can get back from one corner to the other corner using the colors in a different order. And you want those 2 things to be equal because they're a factorization of the same element. So you're forced to look at commuting cubes in when K equals 3, and that gets a little bit complicated, and it's possibly why a lot of people shy away from 3 graphs, because it's really hard condition to check. Okay, so here's a picture of omega 2. There are blue edges running right to left because they have all got degree E1, and red dashed edges going vertically because they have got degree E2. And each square is just a factorization of the 1 into 1 0 0 0 0 and 1 0 1 plus 1 0. And then in a truncated graph, you just truncate this picture like so. And this, I think somebody was asking about how this all got started. Really speaking, this is how it all got started, because we started looking at this, things like this. So every possible way of moving from here to here is identified. So in a way, the morphism from here to here is all these paths, which is why you often find people writing down morphisms in a K-graph as rectangles, just to represent the fact that you can choose any path from one top corner to the bottom corner. That involves a different factorization of its degree. And then for a K-graph, you can define coordinate matrices, which are basically the connectivity matrices of the part of the graph that uses only EI edges. So if you just look at the part of the graph that only uses EI edges, that's a directed graph. And so you just write down its matrix form. And you just notice that coordinate matrices of the graph don't need to be 0, 1. Okay, so here's something I've been pushing for years. get my chance to explain it here. It's a way of getting a 2 graph from 2 1 graphs. So going up dimension. But what's good about it is that data in is something you understand. The data coming out is more complicated, but you have some control over it. You still maintain some control over it. So it's a pair of maps between 2 directed graphs, such that the map from F1 to E1, F0, F0, E1, so just best to look at this picture. You take an element in F, you write down its range and source on the vertical edges, and P of it and Q of it on the bottom. So these are edges in E, and these are vertices in F. And that's something I want you to remember a slide or two in the future. I've picked out some information from E and some information from F. Draw that picture. Are there many textile systems? Of course there are. Textile systems completely determine all possible shifts of finite type in 2 dimensions. So this is pretty general. It's going to be much more general than K-graphs. And so if you're in the business of trying to push the boundary of K-graphs, here's a way of doing it, but yet not losing control of your category. What's important about these textile systems is a lifting property. R path lifting on the range and source path lifting on the source. So basically it says if I've got an edge coming in here and a vertex sitting above it, I can lift that edge up to F in the top graph. And basically, if you've got a pair of graphs, all you need is one of P and Q to have some sort of path lifting, and you get a textile system. So that's a fairly low bar. It's not an if and only if, by the way. So here's how you get to a 2 graph. You build a category out of the data as follows. Oh, sorry, jumping ahead of myself. So inside every 2 graph is a textile system. You just let E lambda be the directed graph using which uses some vertices lambda 0 and edges E1, and you let F lambda have vertices lambda E2 and edges E1 lambda E1 plus E2. And you can convince yourself that you can define a textile system from there. The uniqueness of that map that you've got to have for a textile system is the factorization property. And then there's a notion of a dual textile system. So basically you can jumble up F and E. You can put the vertices together and the edges together and use P and Q as the source and range maps, that directed graph. And then P and then R and S become the morphisms. So this is what's called the dual textile system. And basically what it does, thanks to Elizabeth for getting me right, what it does is take that square I've told you and flip it around the diagonal. And then another way of getting a directed graph that involves a textile system is just take a single automorphism of a directed graph and just use the identity map and the automorphism as your maps, and you get a textile system. So there's example of a 2 graph containing information about the action of a graph on the action of a group on a K graph. Oh, sorry, a single automorphism. Z. So what happens if you start with just a textile system? Well, I've already given you a little bit of a hint by looking at that square. E1 edges on the top, vertices on the side. So what you do is that you define a color graph, a 2-color graph, where the vertices are the vertices from E0 and the edges are edges from E1 and vertices 0. So you throw in the data F into the edges. And the range and source of E is okay, so that's a settled thing, but the range and source of F0 is you have to use P and Q. It'll just drop your vertex onto a vertex of the graph E, so that's good. And then suppose you're a textile system and look at the corresponding collection of squares you got. So what are those collection of squares? They're exactly the square I drew a minute ago with the RF and PF on them. Then that collection is a complete collection of squares if and only if P has unique R path lifting and Q has unique S path. So there is some at work there. You're not going to get complete collection all the time, but look out for it. And this generalizes to high dimensions. So now you've got K-graphs and two morphisms between them. Then you can construct a K+1 colored graph with squares C, which are colored and associative for free. And that's a big deal. So you can just use the textile system, probably the textile system, to guarantee associativity of the squares. And so you can construct a K+1 color graph, which is complete and has the associativity condition, will give you a K+1 graph. Also, it's amusing to observe that a one graph is just consists of two sets of points with range and source maps as playing the role of P and Q vertically. So it all fits together nicely. Now, I'm making a big deal of this thing because you see squares like this all the time in your work and in K-graphs, and whenever I see a commuting square now, I wonder if it's a factorization problem. So that's how badly trained I've become. So there's something called Wang tiles, which are basically colored tiles where you have colors on the tops and bottoms, and no horizontal edge has the same color as vertical, and vice versa. So it's got a well-defined top and a well-defined side. And here's the Wang tile corresponding to a square in a textile system. And so the collection of Wang tiles is just the colors of this textile system. I just E1, union F0. So you've seen that already in the construction. And what's interesting is that you can work backwards. If somebody came up to you with a set of Wang tiles, you can check whether it's a textile system. It'll always give you a textile system. And there's a construction for that. Here's an example. Here's a collection of Wang tiles called domino tiles. So what do you think? What do you do? You have to think of a domino that's being cut in half. And so it's got three of the original edges and one scruffy bit. So here's a tile where this edge has been. That's where the cut happened. And it's got a partner here, which is the other half of the same tile, and the same now for a horizontal version of the same tile, or the same domino. It's well known in high-dimensional, two-dimensional dynamical systems that will obviously tile the plane. You almost need no convincing that dominoes can tile the plane. So this is a shift of finite type. So it should have a textile system. What textile system has it come from? It comes from here. Here it is. Top graph has 1, 2, 3, 4 edges, 4 squares. Remember, the edges, squares are labeled by the edges of the top graph. So this is what I meant by keeping control of the output. You've got a natural parameterizing set for the squares. And that will allow you to compute the homology group and various other things quite easily if you want to. So there it is. That's what the construction gives you. And you can check that that's not a K-graph. Unfortunately. Basically, there's too much. There's 3 edges coming in here. It's big trouble. Compared to the 2 over there. So if you've got a collection of Wang tiles, they come from a textile system, then they tile the plane if E and Q have R and S path lifting. Now, a lot of people interested in textile Wang tiles, particularly interested in question of aperiodic tilings. They're interested in a collection of tiles which can tile the plane aperiodically. Any tiling is aperiodic. That's not actually the sort of thing that we tend to be interested in higher rank graphs, because our tilings are going to be very pure, have lots of periodic points. So that completely rules them out of the game for the smallest set of Wang tiles. Where are the 2 graphs? Well, you've already seen where the 2 graphs are by the result a few minutes ago, because I told you when you get a complete set of tiles. This is going to be a 2 graph. So the basic theorem basically says that you get a 2 graph from this textile system if and only if P has unique R path lifting and Q has unique S path lifting. So here's a way of getting 2 graphs out of a textile system, but something more if you're interested. You can generate interesting monoids from this picture by the bottom graph having a single vertex. We did that a minute ago. So this resulting 2 graph here is going to have a single vertex. It's going to be a monoid. So again, you've got a chance of defining monoids that are have potentially interesting properties, as long as you've chosen your top graph in a smart way. Now, Robertson Steger, I wanted to say something about this. So Robertson Steger produced this definition and some results back in 1999, and they had it set up using just matrices. And so to take K matrices, A by A is an alphabet, and they satisfy a bunch of conditions. The last 2 conditions are not terribly necessary for them being a K graph. So first of all, each MI is non-zero. They commute, and most interesting of all, they triple product and the double product are 0, 1, which is kind of hard for a set of matrices to do. Examples they were dealing with happen to have that property, but this is a tricky condition. And then this next condition is to do with the resulting graph being very, very well connected, and this is to do with it having lots of periodic points. I've already butchered the original definition. So there used to be a condition just H1, but H1 was kind of difficult to check, and they realized this, so they replaced it by these 3 conditions which imply it.
Excuse me,
Yes.
Can you explain H1? What does it mean, not periodic?
Okay, so I'm going to need to draw a picture. So they use this data to, I think it's going to be on the next page, but it uses data to fill in a rectangle where the adjacency is determined by these matrices, just like in a Markov chain.
Okay.
And then basically what they're doing is that saying that each possible size, there's a size that's not periodic. So what they're doing is asking for this p block not to be repeated here or here. So this condition will give you a period with all positive numbers, and this condition here will give you a period where some of the coordinates are negative. So basically, you're asking for all these ways of filling it in to be sufficiently random, so that you can find tiles that don't repeat themselves, and so you can build rectangles that don't repeat themselves. In this sense, when you translate it within a given, a larger configuration. So that's basically the idea, and it's there to control periodic points in the because that's a condition that comes up quite often in C-star algebras, is to be able to control the periodic points, because that swings the resulting structure of the resulting C-star algebra one way or the other quite dramatically, depending on whether the sort of periodicity applies. But what's new is that in 2 dimensions now, we can have a periodicity that involves a shift in the both positive and negative direction. So you get a period that has positive and negative entry.
That has no connection with the period of the matrix. The periodicity of the matrix. Okay.
No, you can't read it off the matrix. Okay, so what do Robert Steger do? They use this, as I've just already said, they use this matrix to fill out rectangles of size M, and then you bunch all the rectangles together to create this object. Oops, what was object W? Now, if you follow Robert Steger, literally these words now contain a declaration. However, it's important not to get confused by that, just to ignore them, and you'll still be fine. I think the decorations were there to help in the C-star context, let's say. And so if you just interested in K-graphs, they're not going to do you any good. So you can just dispose of them. And so you can, just like in a one-dimensional Markov shift, now we've got essentially a k-dimensional Markov shift, but with very special properties because of the zeros and ones. We usually assume that, yeah, the matrices have no zeros and columns, but it doesn't, not essentially important. And a k-graph is strongly connected if you can get from any given vertex to another vertex, as that formula would indicate. So here's something new. I don't think this is in principle. You can form a colored graph from a Robertson-Steger system. So your vertices are A, and you create edges with A, I, and B, where mi of AB is 1. And that's going to be an edge of color I between A and B. And now you do it through all the matrices, you're going to get a k-colored graph with vertices A0. And the connectivity of each colored graph is dictated by the matrix Mi. And the property that Mi and Mj commute when I is not equal to j gives you a bunch of squares. So you just need this B to agree. As you put in the product. that tells you that there's an IJ color graph between A and C. And then if you stare at those conditions hard enough, I will tell you that the resulting K-color graph has complete set of squares, and so you get a complete set of squares, but also you get the associativity condition. Why? Well, the associativity condition is ruled out because of this. This tells you that there's only one cube between 2 points. So checking the associativity condition is not necessary because there is only one way to write down that cube. And so very cleverly, they've managed to finesse the associativity problem with their problems out of their system. And then the condition, second condition tells me if you add in H2, it tells me the graph is strongly connected. So some algebraic examples. Again, this is just a bunch of examples which may appeal to some people for reasons that because of their background. But from my point of view, these were examples of two-dimensional shifts that my supervisor studied, because two-dimensional shifts suffer from a problem of knowing whether such a shift exists. It's a major problem. So what you do is you study ways of making darn sure that your shift space has got points in it. And so this was one of the ways of doing that. So you just take your favorite ring, doesn't have to be Z mod 2Z. A polynomial in the ring, S and T. And then you use its support to define a hereditary subset of n squared. So using all positive powers. So here, for example, the polynomial WST is 1 plus S plus T would make that. So there's an invisible S0 T times T0 here, which is the origin. So we think of that as a tile in n squared. Basically, what you do is you do what you do in it's a finite tile. You look for configurations of zeros and ones, such that whenever you put that tile down, you see a certain pattern. This is what the construction is all about. So just making a note that all these coefficients are 1. There's a 1 has a coefficient 1, T has coefficient 1, and S has coefficient 1. And what we're going to do is we're going to call that stock shape with these weights in the squares, a vertex. And so how many ways can you fill in such a square with a certain property? So we demand that when you fill the square up, you get 0. So 0 times 1 plus 0 times 1 plus 0 times 1 is 0. Good. Here's vertex B. 1 times 1 is 1. 1 times 1 is 1. And 0 times 1 is 1. Then 1 plus 1 plus 0 is 0. And then you run through, those are all the possible configurations you can put in there that satisfy the equation determined by that polynomial. And then borrowing my background in dynamics, you can create a two-graph from this. So you take two vertices and you declare that there's a blue edge from V to U if U overlaps V after a translation by 1 unit in the X direction. So here's a vertex. And here's the next vertex. And if they overlap, so they have to agree here on this 1. And if they can agree, you put an edge between that vertex and that vertex. And you can build a graph from that. And the same goes for red edges, but now you work horizontally. So this is joint work with Ian Rayburn and Natasha Weaver. And then from there you can get, here's the two graphs that you get. That's just built from polynomial and some equation. Now, again, you could generalize this. You could allow yourself to use Laurent polynomials. This is what my supervisor does. He allows Laurent polynomials. But once you start using Laurent polynomials, you get vertices of the wrong shape. So you could get a vertex that's the sock facing this way, and you don't get the factorization property. So again, you're still living within a fairly safe world, but you've thrown away the factorization property. I think I may have to stop there.